Hello everyone, welcome to this sixth lecture session of the course Engineering Thermodynamics. In our previous lecture, we had discussion on the very important thermodynamic properties. So we have actually talked about energy as a very important thermodynamic property which is required in analyzing the thermodynamic system. And in terms of energy, we have divided it into two components, macroscopic and microscopic energy. We found that internal energy comes under the category of microscopic energy, and it's a very important type of energy which is actually can be categorized into multiple four other parts. Okay, and we have also tried to see that what are the different molecular activities which are actually prominent in constituting some particular type of the internal energy. Okay, and then we had discussion on the thermodynamic process and thermodynamic cyclic process. Okay, now from today onwards we will be starting our next module, and in this particular module we will have discussion on the properties of pure substance. Properties of pure substance. Okay, so that is what we have to do. We have to now study about properties of pure substance. So before directly going to the properties of pure substance, let us first try to see that what is a pure substance. So we have to first see what is a pure substance. Okay, so any substance which is having homogeneous chemical composition. Okay, so any substance which is having homogeneous chemical composition, that particular substance is known as a pure substance. So the criteria is substance should have homogeneous chemical composition. For example, if I take water, so water comprises of nothing but H2O molecule. Okay, so wherever you look inside the water, everywhere you will be finding that you will be having only H2O molecule. Okay, so that's why water can be categorized as a pure substance. Another example I can take, say, nitrogen, oxygen. So everything, whatever we are having, where we are having homogeneous chemical composition, that particular thing we call as nothing but our pure substance. Okay, now it doesn't true that it is not true that always for pure substance our component has to be single. Okay, we may have some system where we are having multiple components. Okay, and that multi-component substance can also be a pure substance. Example is air. If I talk about air, particularly in gaseous phase. Okay, so if I talk about air in gaseous phase, what we are having in gaseous phase for air, we have mixture of nitrogen, we have oxygen, okay, and we have many other gases such as CO2, argon, etc. So you will be finding that wherever you go in the atmosphere, wherever you find the air in the gaseous phase, everywhere we will be having same chemical composition. Okay, so if we are having at some one location 77 or 78% nitrogen, we will be finding that at other place also we will be having almost the same composition. Okay, so that's why air, particularly in gaseous phase, can be called as a pure substance. Now if we talk about water, water in all its form, whether it exists as solid or it exists as liquid or it exists as vapor, in each and every form, because chemical composition of the water contains only H2O molecule, so that's why we can call that water is a pure substance in each and every phase. Okay, so whether we talk about single phase, whether we talk about solid phase, liquid phase, or vapor phase, in each and every phase, because we will be having same chemical composition of the water, that's why water can be considered as pure substance in all its phases form. Now, if we talk about air, in case of air, what will be happening? In case of air, in the gaseous phase, everywhere our composition will be same. So that's why in gaseous phase air is nothing but a pure substance. Okay. However, if I talk about air, particularly in liquid phase, so in liquid phase what will be happening? In liquid phase air is not a pure substance. Okay. So why not a pure substance in liquid form? Because what happens, air is comprised of different components. Okay, and each of the component of the air has different boiling point. Okay, so that's why the temperature at which the components of the air will be liquefying, each and every component will be having different temperature, because they are liquefying at different temperature. So because of that, the liquefied air will be having actually different composition. Okay, so that's why we do not consider liquid air as nothing but our this one pure substance. Okay, so it's not a pure substance. Okay, so one more important thing should be there. If we are saying something a pure substance, so it should be miscible. For example, if we are having nitrogen, oxygen, etc., so these are homogeneously mixed inside the air. So that's why everywhere we are having actually same composition. Okay, so for example, if you talk about the mixture of water and oil, so if you take, say, water, and then if you try to mix oil droplets inside this water, what will be happening? You will be finding that after some time there will be a situation where water will be settled at the bottom. Okay, and in the top you will be finding that oil will be actually separating out. Okay, so because oil and water are immiscible, so obviously this type of mixture will not be coming into the categorization of a pure substance. Okay, so now this is about the definition of the pure substance. Now let us try to see the properties of the pure substance. And in terms of properties of pure substance, we will be starting our discussion, say, with by taking into consideration our water as the pure substance. Initially, whatever we will be starting. Okay, one more important thing I would like to highlight over here, that principally substances exist in three different phases. So we are having three principal phases. So the three principal phases are solid, then liquid, and then we have gases. Okay, so these are the three principal phases in which substances exist. Apart from that, we may have other phases apart from these three principal phases. Okay, so that also we will try to see over here. So basically what happens, a phase is nothing but recognized by some particular molecular arrangement. Okay, so if we are having some fixed particular kind of molecular arrangement, that we call as nothing but a phase. Okay, now what we want to do, we want to try to study the properties of pure substance, and let us take the example of water first. Okay, so what I have done, once again I have taken a piston cylinder device, and inside this piston cylinder device, see, this is my piston. I have put certain W amount of weight over this piston, and the this weight is such that it is subjecting our medium inside in atmospheric pressure condition. Okay, and we have water inside this in liquid form. Okay, so water everywhere we are having in nothing but our liquid form. Now what we will be doing, let us consider that at this starting point our pressure is nothing but, we have seen already, atmospheric pressure, and let us consider that temperature is also atmospheric.
Hello,
okay,
sir. Sir, मेरे को कुछ क्वेश्चन पूछना है. Hello, sir. Hello, sir.
Yeah. Yes, Moninder, it is better if we take questions. It is better if we take questions at the end. Okay, so what we have solid, liquid, and gases. So pressure I am considering as P atmospheric, and temperature I am considering as T atmospheric. Okay. Now the idea is let us consider that this because I am saying it as 1 atmospheric, so obviously my pressure will be 1 atm and temperature, say it is 25 degree Celsius. Okay, so now if I take temperature volume diagram, if I take temperature and specific volume diagram, so what will be happening, this is say my point number 1. Okay, so if I plot this point number 1, I'll be having say this as my temperature, and corresponding to that, let us consider this is my specific volume. Okay, so I'm plotting actually over here the diagram in terms of temperature and specific volume. Okay, so this is my point number 1. Now after that, what I did, I have actually taken a burner, and with the help of this burner, now I am adding certain amount of heat. Okay, so now let us consider I have a burner over here, and this burner is actually adding heat into our system. So once we are adding the heat into the system, what will be happening? Because of the heat transfer, our temperature of the system will be increasing. Okay, and one more important thing you have to consider over here, as we are not changing the weight which is acting on the piston, so because of that, what will be happening, we will be having actually same pressure. So pressure will be remaining same at each and every place. However, what will be happening, its temperature will increase because we are adding certain amount of heat. Okay, and because of the addition of the heat, there will be slight expansion of the liquid also. Okay, so we will be having nothing but increase in both temperature as well as the specific volume. Okay, so I have started with a temperature of 25 degrees Celsius. As I'll be adding the heat, this temperature will keep on increasing beyond 25 degrees Celsius. Okay, so say what I have, this is my point number 1, and then because of the addition of the heat, now my temperature is increasing, and at the same point of time, specific volume is also increasing. Okay, so this process will happen till our temperature reaches a value of 100 degrees Celsius. Okay, so this is a very, very important point, because we are having our pressure as nothing but 1 atmospheric, and corresponding to 1 atmospheric pressure, we know that boiling point of water is nothing but, what is the boiling point of water at 1 atmospheric? It is nothing but 100 degree Celsius. Okay, so what will be happening, corresponding to once we are adding the heat, this process of increase of temperature and slight increase of volume will continue till our temperature is reaching to 100 degrees Celsius. Okay, now what will happen after this point? Because at 100 degrees Celsius, we have reached the boiling point of water. So after this moment, what will be happening, if we keep on further adding the heat, our some liquid portion will start converting into vapor portion. Okay, so for example, this is my liquid at the bottom, and then what I'll be finding that I have some small vapors which will be appearing on the top of the liquid. Okay, so this is the transition point at which our liquid has actually started converting into vapor. Okay, so this is one very, very important point. So you can see till 100 degrees Celsius, you are having increase of temperature and slight increase of specific volume. So that's why in this particular zone, you can say that you are having nothing but sensible heating of the medium. Okay, so here we were having sensible heating of the system. Okay, beyond this, because it has reached to the boiling point, after that what will be happening, if you add any further heat, that heat will actually now cause the system or the liquid phase which is there inside to change into vapor phase. Okay, so the conversion from liquid to vapor is nothing but we will be having actually large distance between the molecules. Okay, molecule is water only, but the distance between the molecules will be actually increasing. So that's why what will be happening when we will try to present it on the temperature specific volume diagram, we will be finding that upon the further addition of the heat at 100 degrees Celsius at 1 atmospheric pressure, we will not be having any change in temperature, and specific volume will increase significantly. Okay, so that's why what my line will be representing, that temperature will remain constant, but specific volume is increasing significantly. Okay, so specific volume is increasing significantly. Now this process will continue if we continue on adding the heat, and we will be finding a situation, let me represent it on the next slide. We will be finding a situation where our entire liquid phase has converted into vapor. Okay, so whatever the liquid we were having inside, that whole liquid has now converted into vapor. And once again, we are having our piston, which is there on the top of this medium, and then we have certain W amount. So it means pressure has remained constant, but our entire liquid has converted it into vapor phase. Okay, so now we are having actually complete vapor. One important point you can see over here, while I have drawn the earlier diagram, I am locating piston somewhere over here. Now I have shifted the piston location significantly. It means that once liquid has converted into vapor phase, we are having actually significant change in the specific volume. Okay, so we are having significant rise of the specific volume. Okay, so now you can see over here, if I just plot this process. So what I have done, I have now, let us consider that this is the point corresponding to the complete vapor. So at this point, what we are having now complete vapor, and this is the point at which we were having nothing but our complete liquid. And in between these 2 points, what we will be having here, we will be having actually mixture of liquid plus vapor. So in this zone, in between the complete liquid and complete vapor, we will be having nothing but our mixture of liquid and vapor. Okay, after that, what will be happening after that, if I further keep on adding the heat, what will be happening now, because we have converted our entire liquid into vapor phase, so that's why if I further add the heat, upon further addition of the heat, now what will be happening, we will be having nothing but once again the sensible heating of the vapor. Okay, so after this, if we go beyond this, once again we will be having heating, we will be having number of this one vapor molecules, water molecules in the vapor phase. Okay, and these water molecules will actually keep on increasing their specific volume. Okay, so it means as the temperature will be increasing, density of the medium will keep on decreasing. Okay, so that's why we will be having subsequent increase in the specific volume. So you can see over here, we will be having our line something like this beyond this. Okay, so beyond this, what we are basically doing, as long as we are increasing the adding the more amount of heat, our temperature is increasing, and that increase of temperature is actually causing our specific volume to also increase. Okay, so this line is nothing but once again the sensible heating, and this sensible heating is actually of complete vapor medium. Okay, so that's why you can clearly see over here one important distinction, that while I have plotted the slope of this sensible heating line on this liquid side, it is actually quite steep, and while I am plotting this on sensible heating of vapor phase, there I am showing it as nothing but having lesser slope. Okay, so the reason is this sensible heating line will be having actually this sensible heating line will be having more change of specific volume upon same change of temperature in comparison to. Sarthak, please mute your microphone. Okay, so what we are having over here, in this case, while we are doing the sensible heating, we are doing it for liquid, and here we are doing it for vapor. We know that liquid is nothing but an incompressible substance. So because of that, the change of specific volume in liquid will be less in comparison to the change of specific volume in our vapor. Okay, so the effect of temperature for changing the specific volume in case of vapor will be actually more prominent. Okay, so now one important point you can see over here, that while we have achieved this process over this temperature and volume diagram, whatever I have plotted, over this entire process, our weight which is acting over the piston is constant. Okay, so that's why this is nothing but this entire line is a constant pressure line. So it's a constant pressure line on TV diagram. So this entire line, whatever I have plotted, it's nothing but a constant pressure line on TV diagram. Okay. Now let us try to see a little bit. So now whatever the information I have given in more general form. Now let us try to see more technical details of this TV diagram for defining the properties of water. So let me once again plot this diagram. So I have specific volume along abscissa and I have temperature along ordinate. Okay, and what I am doing over here, this is my line, something like this. This is for sensible heating within the liquid. Then I have phase change portion. Okay, and after that, what I have nothing but my sensible heating in the vapor phase. Okay, and one important characteristic of this entire line is that for this entire line, our pressure is nothing but equal to constant. Okay. Now, what are the different characteristics that we can see over here? So one of the important characteristic is that the point at which our substance is in complete liquid phase and immediately beyond that it changes to vapor phase, this particular point is actually called as saturation liquid stage. So this point is called as saturation liquid or saturated liquid. Okay, so it's saturation liquid state or saturated liquid, and the point over here at which we are having 100% vapor, so that particular point is actually called as saturated vapor. Okay, so what we are having, what we call saturated vapor, the content of vapor beyond which if we just remove start removing the heat, that liquid will start that vapor will start converting into liquid. So that point is referred to as saturated vapor, and saturated liquid is nothing but the state at which we are having complete liquid, but upon further addition of the heat, that liquid phase starts converting into vapor, and in between these two we will be having nothing but this is called as two-phase region. So why two-phase region? Because here we will be having the mixture of liquid and vapor. Okay. Now, what we have, any state which is below our saturated liquid state, that particular state is actually called as either subcooled state. So I can call it as subcooled state, or I can also call it as compressed liquid state. Subcooled or compressed liquid, and any state which is there, any state of the medium which is there above the saturated vapor line, that particular thing is called as nothing but our superheated state. So it is called as superheated state, or it is also called as rarefied state. Okay, so what I have done, I have told you that we are having any state of the medium which is below the saturated liquid point, that particular is called as subcooled state. Why we call as subcooled? Because it requires certain heat to be added in order to reach the saturation point. Okay, and this particular state beyond the saturated vapor is particularly called as superheated, because now it is heated above the saturated point. Okay, and these two states are also called as rarefied state and compressed liquid state. So rarefied is on the vapor side and compressed is on the liquid side. Okay, so why these are called as compressed and rarefied, that we will see in our subsequent discussion while we will be describing the pressure and specific volume diagram. Okay. Now, one important point you have to recall over here, that while we are actually changing our phase from saturated liquid point to saturated vapor point, so during that process actually we are adding certain amount of heat. Okay, so in this process we are adding certain amount of heat. Everywhere we are adding certain amount of heat, all these processes to happen, but particularly in this case, while our state is changing from liquid to vapor, during that time you can clearly see that our pressure and temperature both are remaining constant, and whatever the heat we are supplying, that heat is only employed for changing the phase from saturated liquid to saturated vapor point. So that's why this particular heat is called as latent heat of vaporization. Latent heat of vaporization. Why it is called as latent heat? Because our liquid is changing into vapor. Okay, and the process where liquid is converting into vapor, that process we are calling as nothing but vaporization process. Okay, so that's why we call this as nothing but our latent heat of vaporization. Okay, so now, what we have to do, this is something which we have seen for, say, some pressure P1, and this P1 pressure is nothing but our P atmospheric. Okay, because what I have considered, I have told you that the weight which is I am putting on our piston cylinder device, that weight is nothing but in such a way so that it is subjecting our system to the atmospheric pressure. Okay, now one important point we have to see over here, the process where our liquid gets converted into vapor, this process is particularly referred to as nothing but our vaporization process. Okay, so this process at which liquid changes to vapor, we call this process as nothing but vaporization process. Okay, now the way we are having this one heating, so because of the heating actually our liquid has converted into vapor. Similarly, we can extend this line below also in order to have cooling of our medium. Okay, so this was my point. If I do cooling, then in that case what will be happening, my temperature will fall below 25 degrees Celsius. Okay, and we'll be finding that once our temperature reaches to 0 degrees Celsius, that 0 degrees Celsius is nothing but our melting point of this phase arrangement. Okay, so this 0 degrees Celsius is nothing but our melting point. So now what will be happening at this point, our liquid phase now will be actually converting into the solid phase. Okay, so liquid phase now will convert into solid phase. So this phase transition from liquid to solid is actually known as fusion process. Okay, because here liquid molecules which were having earlier some vibrations, they will be actually fusing to some fixed crystal structure. So that's why the process for conversion of liquid to solid, we call as nothing but our fusion process. Okay, and particularly for water, this fusion process will be happening at our melting point. Okay, and if we go subsequently below till our triple point, then we will be having some situation where our solid, means our ice, will be directly converting into vapor. So that particular point, that particular process is actually referred to as nothing but sublimation process. Okay, so that also we'll try to see subsequently in our property diagrams. Now one important point I would like to take up over here, that I have this TV diagram, and this TV diagram, whatever now I have represented to you all, this TV diagram is nothing but corresponding to some pressure, and that pressure I have called, say, as nothing but my P1 pressure. Okay, so this line is now for some pressure equal to P1. Now what will happen if I start the process with some pressure P2, and this pressure P2 is actually greater than P1. Okay, so in that case, what will be happening? That let us try to see. So now what we have, once again we have the same value of temperature. So obviously I have to start at the same point, but now my pressure is greater than P1. Okay, so now what will be happening, while my pressure is greater than P1, we know that our boiling point is nothing but a function of the pressure. Okay, so that's why if my pressure is increasing, the temperature at which phase change will happen from liquid phase to vapor phase, that temperature will also increase. Okay, so what will be happening when I'll be doing the sensible heating, we'll be having heating which will be continuing, and this sensible heating actually going beyond our temperature of 100 degrees Celsius. So corresponding to P1, my temperature was 100 degrees Celsius. Now it has to go beyond 100 degrees Celsius in order to have our saturation point, because saturation temperature will be now increasing. Okay, so now let us consider this is my new saturation temperature corresponding to T2. So I am calling it as T2 set. Okay, now once we have reached the saturation point, then we will be having phase transition. Okay, and after the phase transition, then we will be having once again superheating. So this is my line corresponding to some higher pressure P2. Okay, now you will be surprising to know that I have while I have drawn this particular line, I have actually made two different arrangement. So one of the arrangement in this particular section you can see, and another arrangement in this particular section you can see. Okay, so what I have done, when I have plotted this point, this saturation point, I have actually slightly plotted it on the right of the point which earlier there was corresponding to pressure P1. And while I have plotted this point over here, this saturation vapor point, this saturation vapor point I have plotted slightly on the left of the point which actually was there corresponding to pressure P1. Okay, so why I have done so? So let me just explain. So what will be happening in case of liquid phase, we know that for this particular region, what will be happening in this particular region, we are having nothing but our liquid, and we know that liquid is actually a incompressible substance. Okay, so if liquid is incompressible substance, so because of that, what will be happening, effect of pressure will be negligible for liquid. Okay, so for pressure, for liquid, effect of pressure will be negligible. So what is the effect of pressure? When the pressure will be increasing, pressure will try to compress our phase. But as our liquid phase is of incompressible nature, so because of that, what will be happening? Over here, pressure will not able to create its impression. So pressure will not be able to decrease the specific volume. However, the temperature has tendency to slightly increase the specific volume. So because of the incompressible nature of the liquid, in this particular case, we will be having actually dominance of temperature. Okay, so we'll have dominance of temperature. Now you can clearly see that corresponding to saturation point, initially our temperature was 100 degrees Celsius. Now, because the pressure has increased, so that's why P2 set will be always greater than 100. So if the effect of temperature is dominant in this zone, so because of that, what will be happening? Because now we are having transition happening, or the saturated liquid point is being obtained at slightly higher temperature than the previous pressure. So that's why what will be happening? This particular point will shift slightly to the right, because this will specify some increase of specific volume. Okay. So over here, this will specify nothing but some increase of specific volume. Okay. Now, if we talk about this particular arrangement, so in this particular arrangement, what will be happening? Over here, we are having nothing but our vapor. Okay, and vapor is a compressible phase. So because of that, for vapor, increase of temperature will try to increase the specific volume, and increase of pressure will try to decrease the specific volume. And as vapor is a compressible substance, so because of that, what will be happening? Pressure will be having dominance over here. So here, pressure will be dominant. So in this particular zone, we will be having the dominance of pressure. Because of that, we will be finding that our point will be actually on high pressure, will be shifting to the left. It means as we will be increasing the pressure, the corresponding to the saturated point, specific volume will keep on decreasing. Okay. Now, if we repeat this particular process for different pressure lines, we will be finding a situation. If I draw temperature over here and specific volume over here, and what I am saying that if I repeat this process for different pressure lines, say this is for P1 pressure, then this is for P2 pressure, and then this is for some P3 pressure. Then let us consider for some more higher pressure. Okay, and what we do, if we just keep on doing this, and if we try to plot the locus of all the saturated liquid points and the locus of all the saturated vapor points, okay, we'll be finding some line like this. So over here, you can clearly see that this line which I have plotted by joining the locus of the saturated liquid points, this will be nothing but my saturated liquid curve. Okay, so this line will be nothing but our saturated liquid curve. And the green line which I have drawn on the right, as it is nothing but representing our saturation vapor point. It is the locus of saturated vapor point. So that's why I may call it as nothing but my saturated vapor line. Okay, and we'll be finding that an interesting observation that these two lines will be actually joining at a common point. Okay, so these two lines will be joining at some common point, and that particular point is actually something which is known as critical point. So this particular point at which these two lines are joining, that particular point is actually known as nothing but our critical point. Okay, and this critical point, why it is called as critical point? Because at this our saturated liquid and saturated vapor line meets, and what will be happening if we go beyond this critical point? You can clearly see that on the left of this saturated liquid line, we are having nothing but a liquid phase. And on the right of this vapor line, we have nothing but our vapor. Okay. But in between, inside this dome, it means in between the saturated liquid and saturated vapor line, we have nothing but liquid plus vapor. But what is happening beyond the critical point? Beyond the critical point, you can clearly see that we have nothing but our liquid is actually directly changing into vapor, because if you draw some constant pressure line beyond that, you will be finding something like this. So it means your liquid is directly changing into vapor, and that is not requiring any amount of heat. Okay, so this particular, that's why this particular point is referred to as critical point, and beyond this, whatever our medium is, that particular medium is referred to as dense fluid. Why it is referred to as dense fluid, that let us try to see. So if we take the case of water, for water, this value of critical point, corresponding to critical point, we have nothing but 22.09 megapascals pressure, and we have temperature of 374 degrees Celsius. Okay, so this value of 22.09 megapascal is actually a very, very high value. So above which, whatever the medium we are having, that medium will be having actually very, very, because pressure is so high, so because of that, the density of the medium will be large. So we call that medium as nothing but our dense fluid. Okay, but the idea is that beyond critical point, it is very difficult to specify the transition from liquid phase to vapor phase, as without even any addition of heat, our liquid immediately transfers into the vapor phase. Okay, however, this particular phenomenon has been nowadays being employed, particularly for generating the power in order to have high efficiency power cycles, and this type of cycles are referred to as actually supercritical thermal power cycles. So that we will try to see in our subsequent lectures. Okay, so now whatever this I have specified you over here, one important point I would like to now highlight. Now, if I plot a curve in between pressure and temperature, and if on this curve I have to draw the saturated vapor line, so my curve will be something like this. Okay, so this will be nothing but my vaporization curve. So you can clearly see that on the left of this vaporization curve, we will be having liquid phase, and on the right of the vaporization curve, we will be having nothing but our vapor phase. So this vaporization curve is nothing but a demarcation boundary from liquid to vapor phase. And one important point I would like to highlight over here, you can clearly see as your pressure value is increasing, with increase of pressure, your saturation temperature, which represents the transition from liquid phase to vapor phase, is also actually increasing. Okay, now if we go below, and what we will be finding, that if we cool this substance, we will be finding some boundary over here, and this boundary will be nothing but corresponding to the transition from solid to liquid. Okay, so that particular curve which represents the transition from solid to liquid, that particular curve is actually known as fusion curve. Okay, and as the boiling point increases upon increase of the pressure, similarly we will be finding that we will not be having much changes in case of our melting point. Okay, so you can see that the temperature is almost same, however pressure is actually increasing. So in case of transition for melting point, with increase of the pressure, there might be slight changes, but the changes will not be very, very significant. Okay, now whatever we have seen over here, let us try to see, let us try to summarize it in few slides. So what I have done over here, as I have already told you that if we plot the PT diagram, then how it will be looking like. Okay. Now, in this particular figure over here, what I have done, I have plotted actually the pressure along ordinate in logarithmic scale. Why I have plotted in logarithmic scale? Because what I have done, I have tried to show the wide range of pressure over here from 10 to power minus 5 to close to 10 to power 4 megapascals. Okay, and temperature I have shown on the linear scale varying from 200 Kelvin to 800 Kelvin. This is the line over here. This particular line, which already I have told you, this particular line is nothing but it is known as a vaporization line. Okay, and on the left of the vaporization line we are having liquid phase, and on the right of the vaporization line we have vapor phase, and here it represents the transition from liquid to vapor. Now this particular line we call as nothing but our fusion line, and this fusion line nothing but represents the transition from solid to the liquid. And if we extend both these fusion line and the vaporization line, these meets a point. That particular point is actually referred to as nothing but our triple point. Okay. So you can see corresponding to triple point, our temperature will be 0.01 degrees Celsius for water, and pressure will be nothing but close to 0.61 kilopascals. Okay, so for water, pressure corresponding to triple point will be 0.61 kilopascal, and temperature will be 0.01 degrees Celsius. Now, at this triple point, if you particularly see what is happening, over here you have vapor, here you have liquid, and here you have solid. So it means if you slightly shift from the triple point, you will be having the presence of all the three phases, and corresponding to this triple point, you can find that all the three phases actually will be coexisting. Okay, that's why it is particularly referred to as a triple point. And if we go below the triple point, we'll be finding that solid will be having direct conversion into vapor. Okay, so that's why this particular line below the triple point is actually known as sublimation line, because the process of conversion of solid into vapor is referred to as sublimation. So the line below the triple point is actually called as nothing but our sublimation line. Okay. After that, I have included a similar diagram for carbon dioxide. So carbon dioxide phase diagram is also included over here. Okay, one important point I forgot to tell you that I have already told you that we are having three different primary phases. So the three different primary phases are nothing but solid, liquid, and vapor. Apart from that, I have told you that depending upon the molecular arrangement, we may have a few more phases. Okay, if we are having some particular molecular arrangement which is homogeneous throughout. So you can clearly see while we are having water in solid phase, there we are having actually the different type of crystal structures which will be forming under different conditions of pressure and temperature. So you can clearly see the phase which is obtained for large range of pressure that we are calling as ICE 1, and other phases are specified as ICE 2, ICE 3, ICE 4, 5, ICE 6 with having different phase boundaries which are also shown over here. Okay, so this is nothing but all these phases of ice, whatever I have shown from 1 to 7, these all are having the same type of same solid. So it is only in solid phase, but the difference is of the crystal structure, okay, or the way molecules are arranged. So that is actually different. So that's why we are representing the multiple phases over here. Okay, now what I'll do, I'll stop at this point, and we will see our further discussion in our next lecture.